There's a visitor in our solar system that has defied all the rules we know. 3I Atlas, an interstellar wanderer from beyond, was supposed to fade into darkness after its fiery encounter with the sun. Instead, it's glowing brighter. Its jet, once pointing away in retreat, has reversed direction. Now, it's aimed back toward the star that should have destroyed it, pulsing with energy that defies every model we've built. Astronomers are watching something that shouldn't be possible: a reawakening. And tonight, I walk you through exactly what changed inside 3I Atlas, and why this reawakening might just be the beginning of what to come. Stay with me until the end. Astronomers around the world had their telescopes trained on a tiny dot of light crawling through the outer reaches of our solar system. The object was called 3I Atlas, and it had traveled from somewhere beyond the sun's gravitational embrace, from the cold space between stars. It was supposed to fade. After its closest approach to the sun in mid-2025, the standard playbook said this interstellar visitor would lose brightness, shed its tail, maybe even fragment into smaller pieces as the solar radiation boiled away its ices. Comets do this. They're fragile things, dirty snowballs that melt and disintegrate when the sun's fire touches them. We've watched it happen countless times. But 3I Atlas didn't follow the script. In early November 2025, fresh images started arriving from observatories across the globe. Instead of fading into the background noise of space, 3I Atlas was glowing brighter than before. Its coma, that fuzzy envelope of gas and dust surrounding the nucleus, had expanded and intensified. Astronomers blinked at their screens. They checked their instruments. They ran the numbers again. The object wasn't dying. It was waking up. You have to understand how strange this is. When a comet approaches the sun, solar heating causes frozen volatiles to sublimate, turning directly from ice to gas. This outgassing creates the classic tail that streams away from the sun, pushed by solar wind and radiation pressure. After perihelion, after that closest approach, the comet moves back into the cold outer solar system. The show is over. Activity drops. Brightness fades. The comet goes quiet. 3I Atlas had just been through that furnace. It had passed within roughly 0.6 astronomical units of the sun, close enough that surface temperatures would have exceeded several hundred degrees. Any normal comet would be exhausted, its volatile reserves depleted, its structure possibly compromised. Yet here it was, post-conjunction, emerging from behind the sun with renewed vigor. The jets were firing again. The tail was active. Something had changed fundamentally about this object's behavior. But the real shock wasn't just that it had brightened. It was the direction of its jet. Standard comet physics tells us that jets erupt away from the sun. The geometry is straightforward. Solar radiation heats the surface, facing the star. Volatiles escape, and momentum carries that material outward into space, away from the heat source. But observers measuring 3I Atlas noticed something deeply wrong with its jet orientation. Analysis of the imagery suggested the primary jet was aligned at approximately 107 degrees relative to the sun's direction. That's not away from the sun. That's essentially toward it. Imagine a fire hose pointed at a bonfire instead of away from it. Imagine a spacecraft venting exhaust directly into the wind instead of using it for thrust. The geometry made no sense under conventional models. Several research teams independently confirmed the measurements, ruling out instrument errors or observational artifacts. The jet was real, and it was oriented in a way that violated basic expectations. This is where the mystery begins to take on weight. Comets are supposed to be predictable. We've been studying them for centuries. We understand their mechanics, their composition, their life cycle. 3I Atlas was now showing us that our understanding might be incomplete, or worse, that this object might not be what we think it is at all. The timing compounds the strangeness. 3I Atlas had emerged from solar conjunction, that period when it was too close to the sun in the sky for ground-based telescopes to observe it. For weeks, astronomers had lost track of the object, blinded by the sun's glare. When visibility returned, they expected to find a fading ember. Instead, they found something that appeared recharged. The metaphor is almost too neat, too convenient. The sun, which should have been this object's executioner, seemed to have energized it instead. Think about that for a moment. An interstellar visitor, something that has traveled for potentially millions or billions of years through the frozen void between stars, arrives in our solar system and behaves exactly opposite to how physics predicts. It doesn't fade after its solar encounter. It brightens. It doesn't orient its jets away from the heat source. It aims them toward it. Every expectation is inverted. So, what are we looking at? The mainstream explanation would suggest some unusual but natural process. Maybe there are buried volatile reservoirs that got activated by deep heating. Maybe the object's rotation or internal structure creates unusual outgassing patterns. Maybe we're seeing a rare but explicable phenomenon that just hasn't been well documented before. Scientists are trained to look for natural explanations first, to exhaust conventional possibilities before entertaining more exotic scenarios. But there's another question lurking underneath the data, one that most researchers won't voice in official papers, but that whispers through conference hallways and late-night emails. What if 3i Atlas isn't entirely natural? What if we're watching something that was designed to behave this way? What if the solar passage wasn't draining it, but powering it up? The implications of that question sprawl out in directions that make some scientists deeply uncomfortable. If 3i Atlas is artificial, if it's some kind of probe or craft from another civilization, then everything about its behavior starts to make a different kind of sense. A sun-facing jet might be a thermal management system, or a solar sail, or a power collection mechanism. Renewed brightness after perihelion might indicate systems coming online rather than ices sublimating. The whole framework shifts. We're going to investigate this properly. We're going to look at the observational data, the composition anomalies, the jet geometry, and the broader implications. We're going to ask what the evidence actually shows versus what speculation suggests. We're going to explore both the natural explanations and the ones that push into stranger territory. Because here's the truth. 3i Atlas is the third confirmed interstellar object to visit our solar system, and it's the strangest one yet. And whether it's a cosmic oddball or something far more significant, it's forcing us to reconsider what we think we know about the universe around us. What exactly did the sun wake up out there? The list of oddities keeps growing. When astronomers compile observational data on 3i Atlas, they're not finding one or two quirks that can be explained away with minor adjustments to existing models. They're finding a constellation of anomalies that, taken together, paint a picture of an object that doesn't fit comfortably into any known category. Each anomaly on its own might be interesting. Combined, they become something closer to a warning sign. Let's start with the jet geometry, because it's the most visually striking problem. Measurements from multiple observation campaigns place the primary jet at roughly 107 degrees toward the sun's position. To understand why this matters, you need to grasp how comet jets normally work. Solar radiation heats the nucleus unevenly as the comet rotates. The warmed areas release gas and dust, creating jets that fountain outward. These jets are always directed away from the heat source, following the basic principle that heated volatiles expand outward into the vacuum of space. The comet's tail then forms as solar wind pushes this material into the characteristic streaming banner we all recognize from photographs. 3i Atlas violates this fundamental geometry. The jet isn't perpendicular to the sun's direction, which might be explained by rotational effects or surface topology. It's pointed toward the sun. That requires a mechanism that either defies conventional physics or involves processes we haven't seen before. Some researchers have proposed that maybe we're observing reflected light or some unusual dust scattering pattern that makes it appear as if the jet is sunward when it's actually not. But the data don't support that interpretation. Multiple wavelengths, multiple instruments, all showing the same basic geometry. Then, there's the brightness and tail behavior. Comets typically follow a predictable light curve. Brightness increases as they approach the sun, peaks around perihelion, then declines as they recede. 3i Atlas showed brightness increase after perihelion. Post-conjunction observations from mid-November 2025 revealed not a fading object, but an active one, possibly more active than it had been before. The tail structures were also strange. Observers reported anti-tail formations, structures that appeared to extend toward the sun rather than streaming away from it. These anti-tails exist in normal comets, but are usually faint and short-lived, caused by projection effects when we view the comet's orbit from certain angles. In 3I Atlas, the anti-tail was prominent and persistent. Now we get to the radio detection, and this is where things started generating headlines. In late 2025, the Meerkat telescope array in South Africa detected radio emissions from 3I Atlas. Initial speculation ran wild. Radio signals from an interstellar object sounded like the opening chapter of a first contact scenario. The internet filled with posts suggesting artificial transmissions, alien communications, deliberate signals aimed at Earth. The reality turned out to be more mundane, but still interesting. The radio emissions were identified as hydroxyl radical emissions, OH molecules created when water ice sublimates and breaks apart under solar ultraviolet radiation. This is natural outgassing, not an artificial signal, but the detection itself was notable because it confirmed active water sublimation at significant rates, and the emission strength was higher than anticipated for an object at that distance from the sun. The composition data add another layer of strangeness. The James Webb Space Telescope conducted spectroscopic observations of 3I Atlas's coma, analyzing the chemical fingerprints of the gases being released. What they found was unusual. The ratio of carbon dioxide to water was approximately 8:1, meaning the coma contained 8 times more CO2 than H2O. Most solar system comets show much lower CO2 to water ratios, typically closer to 1:1 or less. Finding a comet so dominated by carbon dioxide suggests it formed in a very different environment, possibly closer to the CO2 ice line in its parent star's protoplanetary disk, or that it experienced extensive processing in interstellar space. Polarimetry measurements revealed something equally odd. When light reflects off the dust particles in a comet's coma, it becomes polarized, and the degree of polarization tells us about the dust particle size, composition, and structure. 3I Atlas showed an extreme negative polarization branch of -2.7%. This value is unprecedented among known comets. Negative polarization branches occur when dust particles have specific size distributions and refractive properties, but -2.7% is far outside the normal range. It suggests the dust around 3I Atlas has optical properties we haven't encountered before. And then, there's the structural integrity question. Comets are fragile. We've watched them break apart during solar approaches. We've seen them fragment into multiple pieces, unable to withstand the thermal stress and tidal forces near perihelion. 3I Atlas survived its solar passage intact. No fragmentation was observed, no major outburst events that might indicate structural failure. The object remained coherent throughout an encounter that should have at least damaged it, if not destroyed it completely. That implies either an unusual internal structure or a composition that's more robust than typical cometary material. There's an automotive analogy that captures the weirdness here. Imagine you have a car designed to slow down when you press the brake pedal. That's the expected behavior, the physics everyone understands. Now imagine the car starts accelerating when you brake, and the harder you press, the faster it goes. That's not just unusual. That's a fundamental violation of how the system is supposed to work. It means either the car has been modified in ways you don't understand, or it was never a normal car to begin with. 3I Atlas is that car. Every major observable suggests processes that don't align with standard comet behavior. The sun-facing jet is the accelerating when braking moment. The post-perihelion brightness increase is the engine revving louder after it should have stalled. The unusual composition and dust properties are like finding the car runs on a fuel that doesn't exist in any known refinery. Taken individually, each anomaly has proposed natural explanations. Maybe the jet is caused by sublimating CO2 vents on the sunward side. Maybe the brightness increase reflects delayed activation of deep ice layers. Maybe the composition is just what you'd expect from a comet born around a different star. Maybe the dust is coated with organic compounds that alter its optical properties. these are all plausible. Scientists are working hard to build models that can account for each observation without invoking anything exotic. But the clustering is what raises eyebrows. It's not one weird measurement that might be explained by instrument error or observational bias. It's 6 or 7 independent anomalies, all showing up in the same object. That's when you start asking bigger questions. That's when you wonder if the explanation requires rethinking not just comet physics, but the nature of what we're actually observing. Could a sun-facing jet imply deliberate orientation? Could high carbon dioxide ratios indicate synthetic materials or intentional design? Could structural integrity mean metallic reinforcement? The questions sound like science fiction, but they're grounded in real observational data that doesn't fit the models. So, why does any of this matter beyond astronomical curiosity? Because 3I Atlas isn't just another comet. It's a visitor from outside our solar system, and understanding what it is could reshape our entire conception of what's out there in the galaxy. 3I Atlas is the third confirmed interstellar object ever detected entering our solar system. That sentence might not sound dramatic until you sit with it for a moment. For the entire history of human astronomy, for thousands of years of watching the sky, we saw only the sun, the planets, and the objects bound to them by gravity. Comets and asteroids that belong to our local neighborhood. Then, in 2017, an observatory in Hawaii spotted something moving through the inner solar system on a trajectory that couldn't be explained by a solar orbit. The object, eventually named one I/Oumuamua, was traveling too fast and at the wrong angle to have originated from our sun's gravitational well. It had come from interstellar space. Oumuamua caused a sensation. It was the first time humanity had direct observational evidence of an object from another star system passing through ours. The object was strange, tumbling, elongated, accelerating slightly in ways that couldn't be explained purely by gravitational forces. Scientists proposed various natural mechanisms to account for its behavior, but the anomalies sparked speculation that persists to this day. 2 years later, in 2019, amateur astronomer Gennady Borisov discovered the second interstellar object, appropriately named 2I/Borisov. This one looked and acted like a normal comet, with a classic tail and standard outgassing behavior. It was a relief in some ways, evidence that interstellar objects could be mundane, that Oumuamua might have been a one-off oddity. Now, we have 3I Atlas, and it's making Oumuamua look conventional by comparison. Interstellar objects are precious samples. Think of them as pebbles from other worlds, fragments of planetary systems we can never visit, carried to us by the random currents of galactic motion. Every one of these visitors offers a direct physical specimen from beyond our solar system. We don't have to launch probes across light years of space, or wait centuries for a return mission. The galaxy occasionally delivers samples right to our doorstep. 3I Atlas represents an opportunity to study material that formed around another star, material that has been processed by the interstellar environment, material that might tell us things about planet formation and stellar evolution that we can't learn any other way. If 3I Atlas is natural but anomalous, it implies diversity in the population of interstellar objects that we haven't accounted for in our models. The high carbon dioxide ratio, the unusual dust properties, the extreme polarization signature, all of these could indicate that comets from other star systems form under wildly different conditions than ours. Maybe they come from protoplanetary disks with different chemical compositions. Maybe they've been bombarded by cosmic rays during million-year journeys through interstellar space, altering their surface chemistry. Maybe they represent a class of object that doesn't exist in our solar system because our formation environment was too different. That possibility has huge implications for planetary science. We build our models of how solar systems form based largely on what we see in our own backyard. We assume certain ratios of elements, certain temperature gradients in protoplanetary disks, certain processes of accretion and migration. If 3I Atlas shows us that other star systems produce fundamentally different building blocks, then our models need revision. The universe might be more diverse in its planet-forming mechanisms than we've imagined. But there's another scenario, one that most scientists are reluctant to discuss publicly, but that hovers around the edges of every conversation about 3I Atlas. What if it's not entirely natural? What if we're looking at something that was manufactured? The mainstream scientific position is clear. There's no definitive evidence that 3I Atlas is artificial. The anomalies, while unusual, can potentially be explained by natural processes we haven't fully understood yet. Jumping to the conclusion that it's an alien probe would be premature, unwarranted, and frankly damaging to scientific credibility. Extraordinary claims require extraordinary evidence, and we don't have that level of proof. But the question won't go away because the anomalies keep piling up. A sun-facing jet in an interstellar object that brightens after perihelion, composed of unusual materials, showing structural integrity beyond normal comets, all while traveling through our solar system on a trajectory that's being carefully analyzed for any signs of deliberate maneuvering. If you were designing a probe to study our sun up close, what would it look like? Probably something robust enough to survive solar passage. Probably something with thermal management systems that could radiate excess heat, maybe even a sun-facing radiator to dump thermal energy efficiently. Probably something powered by solar collection, devices that would activate more strongly during and after perihelion. This is speculation, and it needs to be labeled as such, but it's informed speculation based on engineering principles and observational data. The point isn't to claim 3I Atlas is definitely artificial. The point is to recognize that calling it definitively natural might be premature too. We need more data, better observations, and a willingness to follow the evidence wherever it leads, even if it leads somewhere uncomfortable. The stakes are enormous. If 3I Atlas is just an unusual comet, it still revolutionizes our understanding of interstellar material and planet formation. If it's something else, if it's engineered or modified or represents some kind of intentional object, then the implications leap into entirely different territory. We'd be looking at evidence of other technological civilizations, proof that intelligence exists or existed elsewhere in the galaxy, confirmation that we're not alone in a universe that has suddenly become far more crowded and interesting. There's a middle ground too, a possibility that's even stranger than simple natural or artificial dichotomy. What if 3I Atlas is a hybrid? A natural comet that was captured and modified by another civilization, turned into a probe or a message bearer, then sent on its way through the galaxy. Science fiction writers have explored these ideas for decades, but now we might be watching one play out in real telescopes. The challenge is maintaining the right balance of skepticism and openness. We can't be so closed-minded that we dismiss evidence because it conflicts with our assumptions. But we also can't be so eager for exciting discoveries that we see alien probes in every unusual data point. 3I Atlas demands careful, rigorous analysis. It demands that we collect every possible measurement, that we rule out instrument artifacts and observational biases, that we build models and test them against the data. It demands honesty about what we know and what we don't. What we know is that 3I Atlas doesn't behave like any comet we've seen before. What we don't know is whether that's because it represents a new natural category or something, beyond our current frameworks entirely. In the coming sections, we're going to dig into the hidden angles, the controversial claims, the speculation, and the science. We're going to look at composition in detail, at dynamics and possible non-gravitational accelerations, at the arguments for and against artificial origins. We're going to place 3I Atlas in the broader context of what we're learning about the universe through recent astronomical discoveries. If you thought comets were simple, dirty snowballs, artifacts of planetary formation that we understood completely, 3I Atlas is here to challenge that assumption. It might be the astronomical equivalent of a spy arriving unannounced at your border, and you're not entirely sure what nation sent them or what their mission might be. The only certainty is that ignoring them isn't an option. What changed out there after the solar encounter? What woke up when the sun's fire touched it? The chemistry doesn't add up. When the James Webb Space Telescope turned its infrared instruments toward 3I Atlas, scientists were hoping to get a detailed breakdown of what was boiling off the object's surface. Spectroscopy can identify chemical compounds by their unique absorption and emission lines, giving us a molecular inventory of the coma. What JWST found was a comet unlike anything in our solar system's chemical catalog. The carbon dioxide to water ratio came in at approximately 8 to 1, meaning for every molecule of water vapor in the coma, there were 8 molecules of CO2. That's extraordinarily high. Most solar system comets show ratios closer to 1 to 1, with water being the dominant volatile. Some comets have slightly elevated CO2, maybe 2 to 1 or 3 to 1, but 8 to 1 puts 3I Atlas in a category almost by itself. Only a handful of comets have shown similarly high carbon dioxide content, and those are generally explained as having formed in unusual regions of the early solar nebula. So what does this ratio tell us? Carbon dioxide ice sublimates at lower temperatures than water ice. In a protoplanetary disk, you'd expect to find more CO2 farther from the star where temperatures are lower, and more water ice closer in where it's warmer. A CO2-dominated object, like 3I Atlas, suggests it formed either in a colder region of its parent disk, or that it has been thermally processed in ways that preferentially removed water. Interstellar space is cold enough that water should be stable, so it's not likely that the journey through the void stripped away H2O while leaving CO2 intact. More likely, the object's parent system had a different composition profile than ours, maybe lower metallicity, or a different balance of elements available during planet formation. But there's another possibility that's harder to dismiss. If 3I Atlas was manufactured, carbon dioxide might have been chosen deliberately as a working fluid. CO2 sublimes at lower temperatures than water, making it easier to manage in spacecraft thermal systems. It's also inert, non-corrosive, and produces gas pressure that can be used for attitude control or propulsion. An engineered object might deliberately carry high ratios of CO2 for functional reasons. The water detection results add more strangeness. Ultraviolet observations found hydroxyl radical emissions, the breakdown products of water, at approximately 3.51 astronomical units from the Sun. That's farther out than most comets become active. It suggests 3I Atlas has a very high active surface fraction, meaning a large percentage of its surface is releasing volatiles compared to typical comets. Studies estimated the active area at over 20%, which is substantially higher than the few percent you'd see in normal cometary nuclei. Most comet surfaces are covered by dusty, insulating material that limits outgassing to specific active regions. 3I Atlas appears to have much more of its surface exposed and venting. This could mean its structure is fundamentally different from normal comets. Maybe it's more porous, with a high void fraction that allows subsurface ices to vent more easily. Maybe its surface refreshes itself constantly, with outgassing dust falling back and exposing fresh ice. Or maybe, if we're entertaining alternative scenarios, it's designed to maximize surface area for thermal exchange or power collection. The polarimetry data remain the most puzzling compositional signature. That extreme negative polarization branch of -2.7% is so far outside the normal range that it demands explanation. Polarization depends on how light scatters off dust particles, which in turn depends on particle size, shape, and refractive index. To get negative polarization that's strong, you need very specific optical properties. One interpretation is that the dust grains are coated with complex organic molecules that have unusual refractive indices. Another is that the grain size distribution is unlike anything we see in solar system comets. A third, more speculative interpretation is that the dust contains metallic or synthetic materials that alter its optical behavior. This brings us to the metal anomaly claims, and here we have to be very careful because the data aren't peer-reviewed yet. Some press reports have cited claims of nickel-rich emissions and unusually low iron content in the dust spectrum. If true, this would be bizarre. Comets do contain metals, but usually in low concentrations, mixed with silicates and organics. High nickel with low iron is not a natural composition profile you'd expect from protoplanetary disk condensation. It's more consistent with processed alloys, materials that have been refined or manufactured. The caveat is enormous. These claims haven't been verified by multiple independent teams. Spectroscopy is tricky, and emission lines can be misidentified or contaminated by other sources. Until the data go through peer review and other groups replicate the measurements, we should treat the metal anomaly as unconfirmed. But if it holds up, it would be perhaps the strongest argument yet that 3I Atlas isn't entirely natural. So what kind of internal structure could produce these observational signatures? If it's a normal comet, even an anomalous one, you'd expect a loose rubble pile, chunks of ice and rock held together by weak gravity, and possibly some mechanical strength from frozen water acting as cement. That structure would be fragile, susceptible to breakup during thermal stress or tidal forces. But 3I Atlas survived perihelion intact, suggesting something more robust. One model proposes a monolithic structure, a single coherent body, rather than a rubble pile. This would give it greater strength, but requires explaining how such a structure forms naturally. Comets are thought to be primordial leftovers from planet formation, agglomerated gently in the outer reaches of protoplanetary disks. Making a single solid body requires either collision and refreezing or some other process that cements the material together tightly. It's not impossible, but it's unusual. Another model suggests a layered structure with different compositions at different depths. Maybe the surface is CO2 rich, while deeper layers contain water and other volatiles. Solar heating during perihelion could penetrate deep enough to activate those buried layers, causing the post-perihelion brightening we observed. The delayed activation would explain why the object appeared more active after the solar encounter than before. The sun-facing jet might be caused by asymmetric venting from specific locations where these deep reservoirs breach the surface. And then there's the engineered structure hypothesis. If 3I Atlas was designed, its internal architecture might include pressure vessels, thermal insulation, structural supports made of alloys or composites. The high active surface area might come from deliberate venting systems. The structural integrity might result from materials stronger than ice and rock. This model requires assuming artificial origin, which most scientists rightly resist without definitive proof. But the model does fit the observations cleanly, which is why it keeps coming up in discussions, despite the lack of hard evidence. Comparing 3I Atlas to normal solar system comets highlights just how different it is. Typical comets have water-dominated compositions, dust-to-gas ratios around 1, relatively low activity levels, and fragile structures prone to breakup. 3I Atlas has carbon dioxide-dominated composition, a high active fraction, unusual dust properties, and apparent structural robustness. It's an outlier on multiple independent metrics. The question becomes, is it an outlier because interstellar objects are inherently more diverse than solar system objects, or is it an outlier because it's not a comet at all? The data don't give us a clear answer yet. What they do give us is a set of constraints that any successful model must satisfy. The model must explain the CO2 dominance, the active surface fraction, the polarization signature, the structural integrity, and ideally the metal anomalies if those are confirmed. No current natural model explains all of these simultaneously without adding special conditions or assumptions. That's not proof of artificiality. It's evidence that our understanding is incomplete, that we're encountering something outside our usual experience. Whether that something is a new class of natural object or something more exotic remains the central question driving the investigation. But composition and structure only tell part of the story. To really understand 3I Atlas, we need to look at how it moves, how it orients itself, and whether its dynamics show any signs of intentional control. The geometry is all wrong. We need to go back to first principles for a moment, to the basic physics that govern how comets behave when the sun heats them. Solar radiation arrives at a comet's surface, warming the material. Frozen volatiles, trapped in the porous ice rock matrix, absorb that heat and undergo sublimation, transforming directly from solid to gas without passing through a liquid phase. The gas expands outward, dragging dust particles with it, creating jets that fountain from the nucleus. Because the heat comes from the sun, and because the comet is rotating, these jets tend to point away from the solar direction, following the local normal of the heated surface. This is why comet tails always point away from the sun, regardless of the comet's direction of travel. The tail isn't like exhaust from a rocket, trailing behind the direction of motion. It's pushed by solar radiation and solar wind, creating a banner that streams anti-solar. Every textbook diagram shows this. Every observation of every comet in history has confirmed this basic geometry. except 3i Atlas apparently didn't get the memo. Measurements place the primary jet at roughly 107 degrees relative to the sun's position. That's not quite directly toward the sun, but it's far closer to sunward than should be possible under standard physics. Some researchers have tried to explain this by invoking complex rotation states or surface topology that creates unusual outgassing patterns. Maybe the jet we're seeing is from a vent on the opposite side of the nucleus, with the gas somehow being channeled or reflected to produce the observed geometry. Maybe projection effects are making a normally directed jet appear sun-facing when viewed from Earth's perspective. But those explanations require increasingly contrived scenarios. Multiple observation epochs from different viewing angles all show the same basic result: a jet component that has a strong sun-facing orientation. That's not something you can easily explain away with projection effects or unusual rotation. It implies either a fundamentally different outgassing mechanism or an intentional orientation maintained by some kind of attitude control. The anti-tail structures add to the confusion. Anti-tails are known phenomena in comet physics, caused when dust particles orbit the comet nucleus in the orbital plane, and we view them edge-on, creating the illusion of a tail pointing toward the sun. But anti-tails are usually faint, short-lived features. In 3i Atlas, observers reported prominent anti-tail structures that persisted across multiple observation periods. That suggests more than just an optical illusion from viewing geometry. It suggests ongoing processes that create sunward-directed material streams. Now we get into the question of non-gravitational accelerations, and this is where the comparison to one I/Oumuamua becomes relevant. Oumuamua showed small but measurable deviations from a purely gravitational trajectory. The object was accelerating slightly in ways that couldn't be explained by the sun's and planets' gravity alone. Scientists proposed various mechanisms, most notably outgassing creating a rocket effect, though Oumuamua showed no visible coma or tail. The debate continues about what caused those accelerations. 3i Atlas is also being watched for any signs of non-gravitational effects. The trajectory is being monitored precisely, looking for deviations that might indicate thrust from outgassing or other mechanisms. So far, the data are inconclusive. There are hints of minor accelerations, but the uncertainties are large enough that they might just be measurement noise. More observations over longer baselines will be needed to say definitively whether 3i Atlas is showing powered acceleration or just following a purely gravitational path with outgassing perturbations. But the possibility looms large in everyone's minds. If clear, consistent non-gravitational accelerations are detected, especially ones that can't be explained by simple outgassing, that would strengthen the case for something unusual going on. It would suggest the object has some degree of control over its trajectory, which is a hallmark of intentionality. Let's explore the speculative mechanisms people have proposed to explain these dynamics. On the natural side, you could imagine buried volatile reservoirs that got activated by deep heating during perihelion. Maybe the solar radiation penetrated deep enough to warm subsurface ice layers, and now those layers are venting with enough force to create unusual jet geometries. Maybe the venting is concentrated in specific regions due to the object's internal structure, creating asymmetric thrust that manifests as odd jets and trajectory perturbations. Another natural mechanism involves thermal cycling and stress. Perhaps the rapid heating and cooling during solar passage created fractures in the nucleus, opening new vents that hadn't been active before. These new vents might be oriented differently from typical outgassing sites, possibly even facing sunward if they formed on that hemisphere. The post-perihelion brightening would then be explained by these newly opened vents releasing fresh material. There's also the possibility of solar-driven charging effects. When a comet gets close to the sun, it's bathed in intense ultraviolet radiation and charged particle streams. This can create electric potentials on the surface, possibly leading to electrical discharges or corona effects. If 3i Atlas has unusual surface properties, maybe metallic inclusions or highly conductive materials, these electrical effects could be enhanced, creating plasma jets or field-aligned outflows that don't follow normal sublimation geometry. On the engineered side, the speculative mechanisms become more dramatic, but in some ways simpler. A sun-facing jet in an artificial object might be a thermal radiator, designed to dump excess heat collected during perihelion. Spacecraft need to manage thermal loads, and if you've just passed close to the sun, you're carrying a lot of heat energy that needs to be radiated away. A sun-facing radiator maximizes cooling efficiency by radiating into the hottest environment, exploiting the temperature gradient. Alternatively, the jet could be a solar sail mechanism. If the jet is actually a highly reflective surface or a stream of reflective particles, it could generate thrust by reflecting solar photons. This would explain why it's oriented toward the sun, as that's the optimal geometry for light sailing. The renewed activity after perihelion might indicate the sail deploying or becoming active after collecting enough solar energy. There's even a propulsion scenario where the sun-facing jet is an exhaust plume from some kind of thermal rocket engine. Maybe 3I Atlas collected solar energy during perihelion and is now using that stored energy to power a propulsion system. The brightening and jet activity would be side effects of active propulsion, with the sun-facing orientation maintained for optimal thrust vectoring. These scenarios sound like science fiction, and they are highly speculative, but they're grounded in real engineering principles and observational data. The point isn't to prove that 3I Atlas is definitely artificial. The point is to show that the observational data don't rule it out, and in some ways, they're more consistent with engineered explanations than natural ones. The scientific community is divided, though not evenly. Most astronomers who've looked at the 3I Atlas data conclude it's a natural interstellar comet, albeit an unusual one. They acknowledge the anomalies, but argue that unusual doesn't equal artificial. The universe is vast, planetary systems are diverse, and we've only observed a handful of interstellar objects. Expecting them all to fit neatly into categories defined by our solar system's limited sample is naive. Of course they're going to be weird. Weird is what we should expect, but there's a vocal minority, led by prominent figures like Harvard astrophysicist Avi Loeb, who argue we're being too quick to dismiss the possibility that 3I Atlas might be something other than a natural comet. Loeb has gained notoriety and significant criticism for suggesting that previous interstellar visitor, 1I/Oumuamua, might have been an artificial light sail rather than a comet or asteroid. Now he's turned his attention to 3I Atlas, and he sees even more reasons to ask difficult questions. Loeb points to what he calls 10 anomalies, though other scientists dispute whether all 10 are genuinely anomalous or just poorly understood natural phenomena. One commentary noted that of Loeb's 10 claimed anomalies, only about 4 have mainstream planetary scientists genuinely interested and concerned. The others are dismissed as either measurement uncertainties, misinterpretations of data, or problems that have reasonable natural explanations once you dig into the details. So, what are the claims that fall into that genuinely interesting category? The jet geometry is one. Even skeptical scientists admit the sun-facing jet is strange and deserves better explanation than we currently have. The composition anomalies, particularly the extreme CO2 ratio, and the polarization signature, are another. These don't have obvious natural parallels in known comets. The structural integrity and lack of fragmentation during solar passage is a third genuine puzzle. And the timing of the renewed brightness, coming after perihelion rather than before, rounds out the list of observations that don't fit standard models comfortably. Then there are the more speculative claims that generate headlines but lack solid evidentiary support. The trajectory claim suggests 3I Atlas approached the solar system along the ecliptic plane, the disk where most planets orbit, rather than from a random direction. Some interpret this as evidence of intentional navigation, arguing that a probe designed to study our solar system would naturally approach along the plane where all the interesting planets are located. But critics point out that the ecliptic alignment isn't as precise as claimed, and statistical analysis of 3 known interstellar objects isn't enough to determine whether their approach angles are truly anomalous or just random chance. There have been claims about radio signals at 1,420 MHz, the famous hydrogen line frequency that SETI researchers monitor because it's a natural choice for interstellar communication. Some online posts suggested 3I Atlas was emitting pulses in a Fibonacci sequence pattern, which would be a clear sign of intelligence. But no peer-reviewed papers have confirmed this. The meerkat detection was hydroxyl radical emission, natural outgassing, not structured communication signals. The Fibonacci claims appear to be internet speculation without observational backing. The metal anomaly claims sit in uncertain territory. Reports of nickel-rich emissions with unusually low iron content would be smoking gun evidence if verified. Refined metallic alloys don't occur naturally in the ratios being suggested, but the data haven't been peer-reviewed, and spectroscopy can be ambiguous. Until independent teams replicate the measurements, the metal claims remain unconfirmed. So how should we evaluate all these competing claims? There's a framework for thinking through extraordinary assertions. First, check the data source. Is this coming from a peer-reviewed journal, a press release from a reputable observatory, or a blog post with no citations? Second, look for independent confirmation. Has more than one team using different instruments measured the same effect? Third, consider whether the anomaly requires exotic explanations or whether it fits within expanded, but still natural models. Fourth, maintain awareness of your own biases. Are you seeing patterns because you want to find something extraordinary, or because the data genuinely demands it? Applying this framework to 3I Atlas gives a mixed picture. The jet geometry, composition anomalies, and structural integrity are well documented by multiple sources using different observational techniques. They're genuine puzzles, but they don't necessarily require artificial explanations. Scientists are actively working on expanded natural models that might account for these features. The radio communication claims and Fibonacci patterns don't hold up under scrutiny and should be dismissed. The metal anomalies are intriguing, but unconfirmed, deserving a wait-and-see approach. But here's where the controversy deepens. Even if we accept that each individual anomaly can potentially be explained naturally, the clustering remains troubling. The odds of one object showing 6 or 7 independent anomalies all at once, even if each has a low probability natural explanation, start to look increasingly unlikely. It's like flipping a coin and getting heads 10 times in a row. Sure, it's possible. Each individual flip has a 50-50 chance. But the cumulative probability of that sequence makes you wonder if maybe the coin is weighted. This is where the philosophical divide appears. Some scientists say we should always default to natural explanations until absolutely forced to consider alternatives. The history of astronomy is full of phenomena that initially seemed inexplicable, but turned out to have mundane causes once we understood the physics better. Jumping to artificial explanations prematurely damages scientific credibility and wastes resources chasing phantoms. Other scientists, including Loeb, argue that we're being dogmatic. They say the prejudice against considering artificial origins is so strong that we'll twist ourselves into knots inventing increasingly complex natural explanations rather than simply acknowledging that artificial is at least a hypothesis worth investigating. They point out that we've spent decades searching for signs of extraterrestrial intelligence through SETI, but when something potentially artificial shows up in our own solar system, we refuse to take it seriously. The truth probably lies somewhere in the middle. We should investigate natural explanations thoroughly, because they're more likely and better grounded in physics we understand. But we shouldn't categorically rule out the possibility that 3I Atlas is artificial, just because that conclusion makes us uncomfortable. Science works best when we follow the evidence, rather than our assumptions. So let's play out the scenarios. What if 3I Atlas is natural, but represents a new class of interstellar comet? That would mean our models of planet formation and comet composition need expansion. It would tell us that other stellar systems produce objects with very different chemistry and structure than we see locally. That's scientifically valuable, potentially revolutionary, for understanding galactic chemical evolution. It would encourage us to study more interstellar objects when they appear, building a statistical sample that reveals the diversity of planetary system building blocks. What if it's artificial, some kind of probe from another civilization? The implications explode outward in every direction. It would confirm we're not alone in the universe. It would suggest technological civilizations are common enough that their artifacts occasionally drift through interstellar space. It would raise questions about the probe's purpose, its age, whether it's still functional or just ancient wreckage. It would transform humanity's self-conception overnight, ending the cosmic loneliness that has defined our species' entire history. There's a third scenario that's stranger than either pure natural or pure artificial. What if 3I Atlas started as a natural comet, but was captured and modified by another civilization? Maybe it's a messenger, carrying information or even biological samples. Maybe it's a derelict, abandoned technology from a civilization that no longer exists. Maybe it's a von Neumann probe, designed to self-replicate using raw materials it finds in each star system. These hybrid scenarios sound like science fiction, but they're logically possible, and some of them might explain the mix of natural and anomalous features better than either pure category alone. The data we need to resolve these questions are coming but slowly. More JWST observations will refine the composition measurements. Radio telescope arrays are continuing to monitor for any signals. Trajectory tracking will determine whether non-gravitational accelerations are real. There's even been discussion of sending a probe to intercept 3I Atlas, though the delta V requirements make that extremely challenging with current propulsion technology. In the meantime, we're left with uncertainty, and that's deeply uncomfortable for scientists trained to reach conclusions based on evidence. 3I Atlas occupies a liminal space between the known and the unknown, between natural and potentially artificial. It's forcing us to confront our assumptions about what's out there and what we might encounter as we look deeper into the cosmos. And regardless of what it ultimately turns out to be, the questions it raises are already changing how we think about interstellar visitors. 3I Atlas didn't emerge from nowhere. It came from somewhere specific, some star system we can't identify, formed in an environment we can't directly observe. But we can understand the broader cosmic context that shaped its origin, and that context is changing in ways that might make objects like 3I Atlas increasingly rare as the universe ages. Recent observations from the Euclid Space Telescope and data from the Herschel Space Observatory have mapped the universe's star formation history with unprecedented precision. What they've found is a story of cosmic decline. Star formation in the universe peaked approximately 10 billion years ago, when the cosmos was only a few billion years old. Back then, galaxies were forming stars at rates 10 to 100 times higher than we see today. The universe was younger, denser, richer in the raw materials needed to build stars. Since that peak, star formation has been steadily declining. Today's universe produces new stars at only a fraction of the rate it once did. The available gas is being used up. Galaxies have already converted much of their material into stars, and the gas that remains is increasingly dispersed and hard to collect. Some projections suggest that within tens of billions of years, star formation will essentially cease in most galaxies. The universe will enter an era of gradually dimming stars, with no new ones being born to replace those that die. Why does this matter for 3I Atlas? Because it tells us something about when and where the object might have formed. If 3I Atlas is old, if it's been traveling through interstellar space for millions or billions of years, it might have originated in an era when the universe was very different from today. Its parent star could have formed in a lower metallicity environment, when fewer heavy elements were available, because fewer generations of stars had lived and died to enrich the interstellar medium with metals. That lower metallicity might explain the composition anomalies. In a metal-poor environment, you'd expect different ratios of elements in the protoplanetary disk. Carbon and oxygen would still be abundant, but heavier elements like iron and silicon might be scarcer. The high CO2 to water ratio could reflect that difference in starting materials. The unusual dust properties, that extreme negative polarization signature, might come from particles composed of different minerals than we see in our solar system's comets. There's also the question of cosmic ray processing. Interstellar space isn't empty. It's filled with high-energy particles, cosmic rays that bombard any object traveling through the void. Over millions of years, this radiation can alter surface chemistry, breaking down complex molecules, implanting hydrogen and helium, changing the optical properties of dust grains. If 3I Atlas has been traveling for geological timescales, its surface has been sandblasted by cosmic rays. The composition we're measuring today might be very different from what it started with. This adds another layer of complexity to interpreting the data. Are we seeing the original composition of 3I Atlas, or a heavily processed version? Did it start with that high CO2 ratio, or did water preferentially escape or get destroyed during its journey? The answers would tell us not just about the object itself, but about the environment it traveled through. The declining star formation rate also has implications for how common interstellar objects might be. Every star system probably ejects material during its formation and evolution. Gravitational interactions between planets can fling comets and asteroids into interstellar space. Stellar encounters can disrupt planetary systems, sending debris on galactic wanderings. With fewer stars forming, the production rate of new interstellar objects should be declining too. 3I Atlas might be a relic from a more productive era, a time when more star systems were forming and ejecting more material. But there's a counterpoint. While new star formation is declining, the accumulated population of old stars and their ejected debris is increasing. The galaxy has had billions of years to build up a reservoir of interstellar objects. So even if the production rate is dropping, the total population might still be growing, or at least holding steady. This makes statistical predictions difficult. How many interstellar objects should we expect to see passing through our solar system? Is 3I Atlas rare, or are there thousands of similar objects we just haven't detected yet? The chemical evolution angle connects to broader questions about galactic history. Our galaxy has been recycling material for billions of years. Each generation of stars takes in gas, fuses lighter elements into heavier ones, then returns enriched material to space when the stars die. This gradual buildup of heavy elements means that stars forming today have much higher metallicity than stars that formed in the early universe. 3I Atlas, if it's ancient, might carry a chemical signature from an earlier epoch, a fossil record of galactic conditions billions of years ago. Reading that record is like cosmic archaeology. We're trying to reconstruct the environment that built this object based on clues in its composition and behavior. The high CO2 suggests certain formation conditions. The unusual dust suggests certain processing history. The structural integrity suggests certain building materials. Each measurement adds a piece to a puzzle depicting a time and place we can never visit directly. There's something almost poetic about it. 3I Atlas has traveled across light years and possibly across eons to arrive here. It's a message in a bottle from another part of the galaxy, from another epoch of cosmic history. Whether it's natural or artificial, it connects us to the broader universe in ways that astronomical observations from Earth never can. We're not just looking at distant light from faraway objects. We're holding a physical sample, even if only through telescopic observation, of material that formed elsewhere and elsewhen. This cosmic context also frames the search for technosignatures. If civilizations are common in the galaxy, they've presumably been arising and falling over billions of years. The peak of star formation 10 billion years ago might have been the peak of civilization formation too. If so, the galaxy could be littered with artifacts from ancient civilizations, technological debris drifting through interstellar space long after its creators vanished. 3I Atlas might be one such artifact, a probe or craft from a civilization that flourished when the universe was younger and then faded away. That's pure speculation, but it's grounded in the cosmological data, showing that the universe's glory days of creation are behind it. We live in a slowly quieting cosmos. The implications for long-term habitability, for the future of intelligence in the universe, are profound. But they also remind us that our moment in cosmic history is specific and perhaps fleeting. The universe won't always be as active and interesting as it is now. 3I Atlas, whatever it is, comes from that broader context of cosmic change and galactic evolution. Understanding it means understanding not just cometary physics, but the history of the universe itself.